सिस्टम इस हरामी की पूजा कर।
क्या तू क्या पाएंगी तो आज तक समझ में नहीं आया
ये सब गलत कर दिए
क्या क्या चल रहा है
ज्वाइन कर लें। कोई प्रोफेसर, कोई लगा दो प्रोफेसर।
हेलो
हेलो, हाँ संतोष सर।
हाँ राजकुमार सर, नमस्कार
हाँ
सर।
सर।
सर स्टार्ट करा जाए?
हाँ, मैं ज्वाइन कर लिया हूँ।
जी,
जब स्टार्ट करना और बताइए।
Good afternoon to all esteemed guests, respected speaker, faculty member and participants. It is an honor and privilege to welcome you all to this faculty development program on the opportunities and challenges in modern power system. Organized by the REC Kannauj Department of Electrical Engineering. We are delighted to have such an enthusiastic group of academician, researcher, and industry professionals joining us for this insightful event. It is my distinct honor to introduce Dr. Rajkumar Patel, sir, an assistant professor in Department of Electrical Engineering at REC Sonbhadra. Dr. Patel earned his PhD from AKTU in 2018 under TCube Research cum Teaching Fellowship. He began his career as an assistant professor as well as research and development. He began his career as an assistant professor in SCST Mathura in 2006, and he has more than 15 years of experience in teaching as well as research and development. In addition to his academic contributions, Dr. Patel has an extensive track record in administrative roles. He currently serves as a Deputy Dean of Student Welfare, Controller of Examinations, among many leadership responsibilities. Dr. Patel has also been recognized with the numerous awards, including the gold medal for his MTech
Recording in progress.
from NIT Hamirpur, the Best Paper Award in various conferences, the and the Best Teacher Award for his contribution to education. He has published more than 25 research articles in the peer-referred journals, 20, and 14 reputed conferences, and one book chapter. He will take a session to topic advanced techniques in fault detection in induction motor. I encourage all participants. Dr. Rajkumar Patel, sir, to begin his session. Sir, please proceed.
Thank you, Mr. Santosh Tripathi, sir. First, let me share my PPT. Then we will start. My screen is visible. Please confirm.
Yes, sir. Sir, visible.
Yes, sir. Definitely,
Okay.
sir.
Okay. So, thank you very much, Mr. Santosh Tripathi, sir. Before I start my topic, I would like to thank Director of REC Kannauj, Professor M.K. Shukla, sir, Head of Department, Mrs. Silpi, and other faculty members to invite me in this FDP. So my topic is today presentation is advanced techniques in condition monitoring and bearing fault detection in induction motor. So induction motor is one of the very you can say key component in industry. So production and all the things basically nowadays depend on this induction motors. So condition of healthy condition of induction motor is very important. If any fault occurs in induction motors, that means that affect the output of the production, which may finally loss in terms of money, which is the my topic will be, my outline will be the introduction and motivation, fault diagnosis using various techniques, and I am using artificial neural network and other feature extraction technique like PCA, and finally conclusion and the differences. So while presentation, if you have any queries, anyone if having any queries, please raise your hand. I will allow through this Zoom setup, then you can ask the question. So what is the introduction? What is the motivation behind this topic is that we know industries nowadays required a very reliable operation now. Okay, throughout the whole life cycle. If machine started and never get fault in that machine, that means that is a very good situation for industry. But that is not happen because of you can say some fault occurrence, and so many reasons are there. Some of those false reasons are like unbalanced voltage. Sometimes it happen. Excessive vibration and noise. Suppose location is there and base something because of the move of the load connection of the load, heavy load, more vibrations are there. Torque pulsation, excessive heat due to overload, and some leakage flux. So these are the mainly reasons. Because of that, there may be faults in the machines. So because of these reasons, we need monitoring of that machine, and that is known as condition monitoring. We will see the definition of condition monitoring also. What is the condition monitoring? So the picture itself says, if you not maintain your machines, if you not take care of machine, it will not work properly. So it is a prime requirement to maintain the condition of the rotating machine which is used in industries. Okay. So what is the basically condition monitoring? Okay. So basically condition monitoring is a maintenance strategy. Okay, that can be you can say involves continuously or periodically. Okay, to the operation of the condition of equipment and machinery. Okay, so the primary goal of this condition monitoring is what? Is to detect the early sign of failure or deterioration which you can observe during the maintenance, or sometimes we can observe to avoid the minimize the downtime. Suppose machine has been fault, so it is the prime requirement is that to clear that faults within a limited of time, so that the output can get properly. Okay, so many techniques in condition monitoring. Okay, those techniques we can say we can do the vibration analysis, we can record the vibration of that machine and analyze those recorded signals to get the what is happening inside the machine. The other one is the thermography. Thermography is very popular one. Basically, it is used near shaft. Okay, because it's a continuous rotation is there. So if anything due to any contamination or anything, there is overheating or some electrical faults or some insulation problem that can be detected by this thermography. Oil analysis. Basically, oil analysis means some foreign contamination maybe in oil. So we can take a small portion of oil and we can analyze those oil by using advanced machines are there. And with the help of those machines, we can find out what is happening with the oil, the time, or how we can say how many time is left to replace that oil. Ultrasonic testing is there, electrical testing is there. Electrical testing basically used for the electrical faults. Okay, so in electrical testing, basically we will use the current, voltage, and resistance to measure, so that we can get the electrical faults or insulation degradation in the machines. Okay, so these are some of the techniques. Some more techniques also there, and with the help of those techniques, we can also now we can know how many life is left with that machine. So that is called remaining useful life, RUL. Okay, so the work is also going on in this area. If machine is having, so how many life is left of that machine? Okay, or there's a technique also. With the help of those techniques, we can increase the lifespan of that machine also. Okay, that ultimately that reduce the financial burden. Okay. So these are the technologies, and with the help of these technologies, we can see all technology we cannot use for all the all type of faults. So some technology with some fault like vibration. Vibration can be used for bearing damage, rotor bar broken, and air gap eccentricity. This is one of the problem. That is MCSA, motor current signature analysis, is used for stator winding also, along with the vibration. The vibration plus one more we can use by we can detect by with the help of MCSA, that is a stator winding, along with the air gap eccentricity, rotor bar broken, and bearing damage. Axial flux is there. So with the help of this, we cannot detect the fault of insulation and bearing damage. Lubrication only we can use in bearing damage, and cooling gap, one of the method that is used for the air gap eccentricity, stator winding, and the insulation. And one last is partial discharge, which is only used for the insulation failure detection. Okay, so these are the techniques which we are using to detect the fault in a machine. Okay, so now one of the important part is maintenance strategy in condition monitoring. So the first is reactive maintenance. There are four types of maintenance strategy. The first is a reactive maintenance. That means we also known as breakdown maintenance. Means once the machine is started, it will use up to the breakdown. Okay, then we will then we will stop the machine, and we can do then analysis of that machine, or we can do the maintenance of that machines. Okay, so for the short term, reactive maintenance is okay, but if in the long run, it is a highly cost effective. You can say, okay, because downtime may be very large, which is not good for the industry. Okay. The other one is the second one is the preventive maintenance. That is basically scheduled maintenance. Scheduled maintenance means we can decide for a particular machine, we can decide a time interval. Okay, for 1 month or 2 months, like that, depending on the use of that machines. Okay, so it will be quarterly, it may be yearly, like that. So depending on the machine application, maintenance, we can make a chart of that machine. Okay, so regular maintenance will be there, or we can say the reduced maintenance, scheduled maintenance. So this is under the preventive maintenance. Okay. So, but in that case, the disadvantage of this preventive maintenance is that the cost of labor is very high. Okay. So, third one is the predictive maintenance. Okay, so predictive maintenance is basically condition-based maintenance, which is the most popular method of maintenance. Okay, in that what we are doing, basically in that we are collecting the information regularly, continuously we are collecting the data from the machines. Like just we have discussed, like we can apply a system, or you can install a system which can record the data like we can record the vibration, we can record the current, we can record the voltage, we can record the oil, you can say oil also, we can take oil sample also. Okay, so from these data we analyze and try to find out what is happening inside the machines. Okay, so this will come under the predictive maintenance. So the disadvantage of this method is that it required a significant amount of investment. Okay, because ultimately we have to install some additional equipment, and those additional equipment will have some extra amount. So this is one of the disadvantage of this preventive. But surely, if we use this type of maintenance, lifespan of the machine will be surely it will be increased. Okay. The fourth one is the proactive maintenance. This type of maintenance basically based on the root cause of equipment failure. Okay, so we are trying to find out the what is the mainly root causes, because of that the fault is happening in that machine. Okay, so this is also required analysis of the taken data from the system. So these four types of maintenance strategy basically we are using in industry. Okay, so what is the condition monitoring process? Okay, so we can start from here. This is we can say the motor fault in various part of the machine, and we can install a sensor which can record these information. This sensor may be vibration, current, temperature, speed, voltage. Then the processing is involved, signal processing involved. This signal processing may be in time domain and frequency domain or time frequency domain, like that. And then we can detect the fault. This fault detection can be ensured by the expert knowledge. If we have some expert knowledge, then only we can decide the fault is in that which type of fault exists in that motor. Okay, so this fault detection may be based on motor-based trending threshold, neural network, fuzzy logic, expert system, and so many nowadays advanced techniques are there. With the help of those, we can decide the type of fault which exists in that machine. Okay. So what is basically this signal processing flow? So this is the, you can say, suppose a motor, and the transistor is there. With the help of this, there's a data collector or analyzer. We can collect the data in the form of waveform, and we can apply some FFT. And with the help of this FFT, we will get some specific frequency. Okay, and if we have expert knowledge about those frequency, we can do some conclusion about the condition of that machine. Okay. So these are some defects which occurs in the machine, like this is winding defect. The second one is a bar defect. This is a rotor defect. So this is a bearing defect. So all these type of defect will reflect through the we can record these information by the sensors. Okay. Now this is one of the analysis. It has done two studies there. One is done in 1985. The reference is given. Another is in 2008. Okay. So these are basically study has been done for bearing, stator, and rotor fault. And we can see that in 1985, the bearing fault is only 41%, and the rest of is stator. The second highest fault occurs in stator, and then rotor, and then other miscellaneous part is there, and that falls exactly in 1985. But you can see in study 2008, which shows that the faults in bearings increased to the 69%, from 41% to 69%, and stator fault is reduced from 37 to 21%. Okay, so this information says that there is a more focus required for analysis of bearing, because its continuous rotation is there, so there is more chances of fault which occurs in bearing. So today's presentation, I will focus on the basically bearing part, faults, how we will detect the faults in bearing. Okay.
कब फोन करके पूछ रहा ये चाहिए मैं फ्री इतना इतना फ्री है ये
basically a bar chart.
तो काम होता है एलडीएम के पास सांस लेने का टाइम नहीं होता जितना आपको पता है
we can say there is a significant
कि तुम उस कैच को पकड़ के तुम उसके पीछे क्यों पड़े हो लटक क्यों गए हो
there is significant increase in bearing
किसी भी
and in stator and rotor and others fault are reducing. Okay,
बस ना लेडीज समझ के आदमी ज्यादा डरवाने की कोशिश करता है.
So what is basically vibrations? Vibration is basically back and forth movement of a structure, any structure. Okay, and it can be referred as a cyclic movement. Vibration is nothing but a cyclic movement. This movement we can divide into basically two parts. One you can say the vertical, and one is we can say the horizontal. Okay, so you can see. So what this transistor actually detects, if this is actual bearing movement, it's a cyclic movement, and we can see the sensor we can mount on the top, or we can mount on the horizontal. Okay, so based on that, if we mount it on the top, the vertical movement it will be detected, and if it is mounted on the horizontally, it will detect the horizontal movement of the that bearing. Okay. Okay. So basically, the signal which is recorded, this recorded signal is basically non-stationary in nature. Okay. There are two types of signal. One is we can say stationary, another is a non-stationary. Stationary signal is we can say the frequency present all the time. Okay.
ऐसा बोलता है ना वो भी नहीं बोल पाएगा अगर तुम्हारे सामने तुम्हारे सर
non-stationary signal
लगेगा बढ़ देती है
and non-stationary signal at different time of different instant of time, different frequency may occur. Okay, so there are two types of non-stationary signal we can identify in the machine. One is the current signal, and the vibration signal is a very strong non-stationary signal, and this current signal is a weak non-stationary signal. Okay, so both the signal, current signal and vibration signal, both signal are non-stationary. But vibration one is the and MCSA is motor current signal is basically a weak non-stationary signal. Okay. Okay. So this is a time waveform. This is from this diagram you can see that the different parts will generate a different amount of different types of waveforms, and we combine all waveform together. We will find a complex time waveform. Okay, so here you can say, suppose this is this structure is basically gear system structure. From there we can say there is a high frequency, and the shaft, the front shaft, the frequency is a little bit low frequency, and if you can say body, there's the frequency is very low frequency. So if all combined together, because finally ultimately the sensor is record all the vibrations. Okay, so if you see the waveform of the overall body vibrations, this will become a very complex time waveform. So this complex time waveform will have various different types of frequency. Okay. So if you talk about the frequency, you can say there are 5,000, 10,000, 50,000, 20,000 hertz frequency is there. Okay, so we can say if 1 RPM one RPM balance 1 RPM frequency is there, that means this, your system is balanced. 2 RPM means alignment, 3 into 5 means looseness. So for every problem, there is every specific frequency of range of frequencies. Okay, so if you see that area, in that area you can analyze the frequency and you can see the nature of frequency. So in that particular range, we can observe the amplitude of that frequency. If the frequency see the x-axis is basically time or days, and y-axis is basically recording amplitude. So the green area is, you can say, the safety area, but yellow area is basically alarming area, warning. Warning means we can go for the preventive maintenance. Okay, and if we cross the red area, it means that the alarming situation, we have to take shutdown of that machine, or we can say we can go for the unplanned downtime. Okay, there are two types of downtime. One is the plan and another is the unplanned. Unplanned is very costly. Okay, plan is we can reduce the cost, you can reduce the loss, but unplanned downtime of the machine is basically it is not good for the industry. Okay, so the high frequency range basically belongs to the bearing damage part. Okay, so in that also we can see the green, yellow, and red area. Red, after that red area, there's an alarming situation. Okay, so up to here we have discussed what we require to do for the condition monitoring of a rotating machines or induction motor. Now I am taking a real-time example to understand how we detect the faults. For that, I have taken data. This data is from it's freely available on the website. If anyone interested to work in this data, they can note down. The address is given. The link is given in this slide. That is Case Western Reserve University bearing data. If you type the same information on the Google, you get the directly data. So this data is basically in the .mat form, mat file. You can access the data in MATLAB. Okay, and this data is recorded on a 2 HP 3-phase induction motor. Okay, the motor on which this recording has been done is 2 HP. Okay, and the sampling frequency of the recorded data is the 12,000 per second. 12,000 samples per second means in 1 second 12,000 sample has been recorded by using of 16-channel digital audio tape, that is that recorder. Okay, the speed variation is from 1,797 RPM to 1,752 RPM, means from no load to full load. Okay, so the recording has been done for from no load to full load at various faults. Okay, for better understanding, you can see this chart. Okay, so when your induction motor is healthy condition and loaded at no load, 1 HP load, 2 HP load, and 3 HP load. 3 HP is basically overloading condition. Okay, 2 HP is normal, and 1 is underloading, and 0 is at no load. Okay, so all 3 load conditions, the record vibration has been recorded. Okay, and the same induction motor has also been recorded when fault seeded to the inner race, rolling ball, and the outer race fault. Okay, what is this inner race, outer race? We will see it sooner. Okay, so suppose inner race fault is there. Inner race fault means that inner race fault is recorded at 0 SP, 1 SP, 2 SP, 3 SP with a fault size of 0.07 inch, 0.014 inch, and 0.021 inches. Okay, so suppose our induction motor is at no load and the fault is seeded the inner race of the bearing. First, it is seeded at 0.07 inch and then recorded at no load. Then again, it is taken out from the machines. Again, fault is seeded at 0.014 size and then again recorded. Again 0.021. So this is a repetitive process. So if you go to the website of that Case Western Reserve University, you will see a plenty of data is there. Okay, so from those data you can see the pattern of recording. Okay, just as I have told you, all data files are in MATLAB.mat format. Okay, and that digital data was collected at 12,000 samples per second. Okay. Okay. So this is now we are going to discuss the fault diagnosis using various methodology. The first methodology which I am using is that is a bearing structure. From here we can say just I have told you there are mainly four parts of this bearing. The first one is the outer race. Okay. The inner part is we say inner race. Okay, and the ball. These are ball. This is known as ball spin, and the structure in which ball is fixed, that is called case. Okay. Okay. So this is outer race, inner race, ball spin, and case. Okay. So suppose anywhere, any places if fault is there, the ball pass from that area, the spikes will be there, and that spikes will be recorded by the transducer, and then finally, with the help of that recorder, we can store into the computer. Okay. So here we can see there's a four recorded signal is there. Okay. The first one is this all recorded signal is from 1 second. 1 second means this is having a 12,000 samples. 12,000 samples is there in each of the figure. Okay. So this first one is A is basically recorded when our induction motor bearing is normal condition, healthy condition. No any fault seeded into the inner race, outer race, or ball. So this is simply a recording. So you can say the flatness is there. There is no much spikes in this normal condition. In B, we can say this is recorded when the fault at inner side. Okay, inner side means the fault is inner side, the inner case, inner race. So if the fault is inner race, this type of, you can say, the signal we can observe. The third one is rolling element fault. A fault in ball because it's continuous rotation, so maybe there is a wear and tear may be observed in the into the ball. Okay, so if wear and tear observed in the ball, it means this type of waveform we can see, we can record, we can see the waveform when the rolling element fault is there. Okay. And the last one is basically this is outer race fault. Outer race fault means a fault seeded into the outer part of the bearing. Okay, so this type of we can see the signals. Okay. So by observing these four signals, if a third person cannot decide anything about this, which type of fault is there. Okay, because they all almost looking very similar. Okay. So what is needed? So we need to analyze these signals. We can take the FFT and others advanced techniques to identify the faults. Okay. So up to now, if any queries, you can ask it. Okay. Let me proceed. Capital GST at the rate of 841. Yeah, Vikas Pandey se पूछो. Sorry, 2021. 2021 at the rate 2021. नहीं अलग बोल के Okay. So now what we are going to take first step. The first step is that we are going to calculate the statistical parameter of these waveforms. Okay. So this is a statistical parameter, list of statistical parameter like first moment, second moment, third moment, and this is also known as mean, variance, skewness, kurtosis, crest factor, impulse factor, margin factor, shape factor. Okay. So if you observe this statistical parameter, you can see that some of the statistical parameter are basically dimensionless, and some are having some dimension. It's depend on the what type of accelerometer you are using. Okay. Now what we are doing We are going, after calculating these all information, we are plotting. We have plotted this information. Okay. So from here we can see there are three conditions. The first one is, the first row is basically healthy condition, and the second one is it's inner rest fault with a 0.07 inch fault size, and the one is inner rest fault with a fault size of 0.021 inch. Okay, so there's a pattern. The pattern is that from healthy to inner rest fault, and the inner rest fault with the size increases. The amplitude increases as the fault size increases. Okay, that indicates that if size will be more, the amplitude of the calculated parameter will be high more. Okay, the same thing you can observe in suppose a machine is there. Today we have recorded some information, some this statistical parameter, and after 1 month you can record the statistical parameter again. And if you compare those information, if you find the gap is there, the difference is there in amplitude, that means you can say that the severity of fault is increasing. Okay, if it is remain constant, you can say that fault is remain at same place, same situation. But if it is increasing, that means the fault size increasing means the fault severity is increasing. Okay, the other point which we can observe is that the dimensionless parameters is more, you can say, impactful compared to mean variance skewness. Okay, because you can see the amplitude is clearly visible. Okay, in case of cortices, crest factor, impulse factor, and margin factor. Okay, the same exercise also has been done for the this is for outer rest fault. Okay, again the first row is healthy condition, the second row is outer rest fault at 0.007 inch, and last one, same information, same we can conclude is that the if fault severity is increases, the amplitude of this statistical parameter will also increase. Okay. Okay. Now again we can see the structure of the bearing. Again, you can see the inner race, outer race, ball spin frequency, and the case FTF. Okay, so that each section of the bearing will indicate a particular frequency. Okay, if fault is suppose fault exists in inner race fault, it will generate some specific frequency. Some spikes is there. That spikes means the frequency. Okay. Similarly, if fault is occurs at outer race, it will generate a specific frequency. And BSF also generates a specific frequency. So it depends, the amount of frequency or the value of frequencies will depend on the structure, basically structure of the bearing. Okay, and in order to calculate that value of frequency, we can get from this formula. Okay, that's the bearing frequency equations. So FTF is FR by 2, 1 minus BP upon BD cos theta, BSF, and this BPFO and BPFI. These are the formulas. Okay, and here is the nomenclature. BP is basically ball or roller diameter. What is the ball is there? What size of ball is there? What is the diameter of that ball? N is the number of ball. How many ball inside the bearing? And this PD is basically pitch diameter of the bearing. Okay, and cos theta the angle, at what angle it's contact with the inner race. Okay, so these are the basically mathematical expression. With the help of these mathematical expression, we can know the value of frequency, and that we need to search that frequency in that signal. If that frequency exists in that signal, that means we can say that particular fault exists in that recorded signal. Okay. So in our case, the case Western Reserve University data center, these are the value of frequencies. BFI is 158.34 hertz. BPFO is 104.76 hertz. BSF is ball spin frequency is 68.89 hertz, and the FTF is 11.64 hertz, and the running frequency is basically 29.23 hertz. Okay, And these are the ball bearing specification. The number of ball is 9, BP is 7.940 mm, PD is basically 39039 mm, and here we have theta considered as a 0. 0 means 1. Simply cos theta is 0 means we have taken as a 1. Okay. Now, in order to search these frequency, we have proposed a method to identification of the defect in the bearing. So what we are going to do, we are going to image that measured signal, that is say ST, and we are going to pre-process. Pre-process means basically to check the alignment is there, to check the variance is there or no. Okay. So basically, we are pre-processing means we are removing the noise. We can say we can remove the noise in that by using filter. We can remove the noise from that signal. Then we are going to use a wavelet transform, one of the popular wavelet form, that is discrete wavelet transform, and we are decompose those signal into the J level, J4 as per your decided by sampling frequency. If sampling frequency is high, you can decompose at a deeper level, and if sampling frequency is low, the decomposition level not more than 2 or 3. Okay. The next criteria is to detect that bearing fault is that selecting the high energy level signal. Okay. So when you decompose the signal by using a discrete wavelet transform, after decomposition, we are going to calculate the energy of each band. Each decomposition level. Okay, so focusing on bands which is having high level of energy. Okay, then we then we will use then we will perform Hilbert transform, one of the popular method to detect the envelope in any time series signal. Okay, and then we will try to we'll try to take spectral analysis and try to search the defect frequencies. Okay. Okay, so this is one of the example. You can see here the signal is decomposing into 2 level. Okay, so after decomposition, we will basically decomposition in the discrete wavelet transform is we are passing through the low pass filter and high pass filter band filters. Okay, and low pass filter again decomposition into 2, that is high pass, low pass. So one wing is going to decompose into 2 frequency bands. Okay, and how we will get this? So D1 is basically 3000 to 6000 hertz. D2 is 1500 to 3000. This passband filter, this filter is basically a range of frequency which is passed through that filter. Okay, 7750 to 1500, 0 to 70. Okay, and these are the signals. Okay, after the passing through the filters, means by using the discrete wavelet transformer. So this is divided into 2 parts. You can see clearly. The first part is basically normal bearing signal, and the second is basically faulty bearing signal. Okay. Faulty means any one of the fault. It may be inner, outer, or spin, wall spin. Any fault is there, that is right hand side. Okay. So magnitude wise, you can say surely there will be fault will be exist, but where it is a fault frequency, that is important to know. Okay. So in order to get the fault information, in which band the fault information will be there, so most probably the fault frequency will be available in that band which is having the high energy. Okay. So we have calculated the energy. You can see the energy. So the first one is the normal bearing, and the second one is the fault bearing signal. So you can observe a pattern. Okay. In that pattern, you can say D1 is in normal bearing D1, D2, D3, and A3. Okay, and in faulty bearing A3, D3, D2, and D1. Okay, so if you observe both normal and faulty, you can say in normal case the D1 is having very low energy. Okay, But when fault occurs, the energy is increased a little bit. D2 also, we can say energy is there, but in fault condition, energy increased significantly. So our interest in this D2 band, because you can see the increase in energy. Okay. Also, we can observe that basically, if you see the shifting of energy, okay, from A3 to D1, D2. Okay, the detailed coefficient, A, the approximate coefficient. Okay, so basically shifting of energy. So what is happening in normal to faulty condition is that the energy is shifting from we can say the high frequency to the lower frequency to the high frequency range. Okay, it means we can say the fault frequency shifting to the high frequency regions. Okay. Okay. So our as per the flow chart, okay, we have to select the higher energy level of signal. So in that case, our D2 is our you can say the important band in which we can search for the fault information. Okay, so what we are going to do, we are going to select this D2 signal, okay, D2 signal, and going to calculate the Hilbert transform. Okay, so Hilbert, what doing basically Hilbert transform? Like basically Hilbert transform shifting our signal by 90 degree, and we can get the after shifting that that signal by 90 degree, we can get a complex value signal. Okay, that is xt plus ixht. Okay, and we can get a very envelope by if you plot this information, we can get
हेलो
हाँ नहीं वो फिर हो गया, मैं कनेक्ट कर रहा हूँ।
सर डिस्कनेक्ट हो गया है क्या?
नहीं सर, कंप्लीट नहीं हुआ है, ये डिस्कनेक्ट हो गया था मेरा।
जी 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 सर जी।
वो कैंडिडेट्स भी डिस्कनेक्ट हो गए हैं पूरे, दिखा नहीं रहे हैं। हाँ ठीक है, आ गया आ गया। Okay, so we are here by using this. We are here up to the proposed methodology. In that we can say frequency. We can clearly observe the frequency of normal condition is FR and 2FR. This is inner rest defect. You can clearly observe by using the proposed method that BFI 3, BFI 4, BFI all four. You can say the frequency is identified in inner rest. So from here we can declare that the taken signal where the proposed method has been applied, and that is successfully detected the fault frequencies. Okay. Okay, this is a rolling element defect. Here also the fault frequency successfully identified, and this is outer rest defect that is also successfully identified. Okay, so from here we can say the proposed methodology is very effective to identify the fault frequency, to declare that the fault exists in that bearing. Okay. In this method, there is a disadvantage that a lot of other frequencies are available except the fault frequencies. That is one of because interpreter whoever is going to interpret this circuit and this waveform or this diagram, they may go mislead. Okay, so it is required to remove these sidebands and to get the only that fault frequencies of innerest outerest. Okay, so another method or modified methodology is identify for the faults, and that is basically what we are going to use. We are going to use a wavelet packet transform. Okay, and in spite of discrete wavelet transform, we are going to use wavelet packet transform, and by using wavelet packet transform, we are going to calculate the one index is there that is called bearing damage index. Okay, with the help of that bearing damage index, we will choose the value which is having higher bearing damage index. Then we apply again in spite of that Hilbert transform, we're going to apply TKO, that is Teacher energy operator, and again we repeat the same process. We'll go for the spectral density and we'll identify the fault frequencies. Okay, so this is the purpose is same, but the method is different. So we can say this is a modified methodology. Okay, so in modified methodology, the first we are going to decompose our signal in wavelet packet transform. Okay, so in wavelet packet transform, what we are going to do? We are going to decompose our signal in both the wings, right wing and left wings. Okay, so in this we will get more number of nodes. Okay, in discrete wavelet transform, we are getting only 4 nodes, but here we are getting 8 nodes. If we go up to the 3 levels, we will get 8 nodes. Okay, and in these 8 nodes, we'll again try to find out which one is having a higher bearing damage index. So this is the formula of bearing damage index. How we are calculating this bearing damage index? Basically, we are going to get a difference between normal bearing, energy and the fault frequency energy for that particular band. Okay, and we are going to plot those information, those energies. Okay, and by using this, we can see most of the energy is existing at you can say D7. Here is the numbering there: 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so A7 approximate signal. So this is A7. Okay, so the difference between healthy condition and faulty condition, there is some energy difference, and that energy difference is mainly at this band number 7. Okay, so what we are going to do, we are going to apply one of the envelope to detect the enveloping, that is a trigger, you can say completer of Hilbert transform, you can say. Okay, so we are going to apply TKU in that A7 signal, and then we will apply the spectral density and again try to find out the fault frequencies. Okay, so with the help of this, now you can see the same information, same results, but little bit you can say better, because in this the sidebands are almost negligible. Okay, compared to the previous results, you can say in this the sidebands are almost negligible. Okay. So you can say this method is modified one, and we can easily decide, and we can take easily decision that the fault is exist in that bearing part or not. Okay, and which type of fault is existing in that way. Okay, so this information this decision can be take more confidently. Okay. Okay, so this is up to here we are able to successfully detect the fault frequency and to detect the where the fault is inside the bearing machines. Okay, in spite of these proposed methods, some of the methods is there where we can visualize the whether fault is exist or not. Okay, so the first one is basically STFT, that is short time Fourier transform. Both the figure we can observe is that the frequency range in healthy condition, the frequency is lower range, but in bearing with defect is yellow area, dark yellow area, we can say shifted to the high frequency ranges. So as we have earlier discussed, what is happening when the fault is occurs, the shifting of frequency from low frequency range to high frequency range. But the same thing we can easily observe in this short time Fourier transform technique. Okay, this STFT, it is already available in MATLAB. You can search for this code STFT and you can directly apply to the signal and you get such type of results. Okay. A similar way is the continuous wavelet transform that is a little bit more advanced compared to STFT because window length in STFT is fixed, but in continuous wavelet transform, the window length is changing as per the when time passes. Okay, along with the time, the window length is changes. So we can use for the non-stationary signal this continuous wavelet transform. Okay, so from here also we can say in healthy condition, the frequency is at lower range, but you go for the bearing with the defect, we can observe the fault frequency at higher ranges. Okay, so basically here also we can observe the shifting of energy, shifting of frequency from low range to a high range. Okay, so but this visualized method, in this visualized method, the disadvantage of this method is that we are unable to find out the which type of fault is there, in which part of the bearing fault is existing. So this is a disadvantage of this visualization techniques of fault detection. Okay. So now up to here we have successfully detected the fault. Now we are moving towards the ANN. Okay, we are going to use artificial intelligence to identify the faults. Basically, we are going to do the classification of faults. Okay, in this case, this is a flow chart of the ANN. This is not basically ANN. Basically, it is a motor fault diagnosis flow chart. This we can say the motor, the first motor, which is a data equation we have already seen. Next is feature extraction. Feature extraction means whatever the signal we have recorded in that signal, we can extract some meaningful information. Okay, so those meaningful information we can say it is a feature of that signal. Okay, then that recorded signal, that extracted feature can be broken into, or you can say divided into two parts. One is a training set and another is testing set. And this testing will goes to the ANN, and from ANN output we can see the classification rate, and we can see the accuracy of the model of the given system. Okay. So what are the feature extraction here? The feature extraction, total 11 features we have extracted. For the same data, case Western University data, we have extracted total 11 features. The same feature we have discussed earlier. And those features are basically mean, median, mode, standard deviation, variance, range, courtesy, viscouses, skewness, crest factor, impulse factor, clearance factor. Again, we can divide into mainly 4 measures: the center tendency, variability, dispersion, and the dimension of dimensionless parameters. Okay, so basically these 4 types of measures features are there. Okay. Now we can plot these features with respect to each other. We can see the basically distribution of features we have calculated from the signal. Mainly 6 features here. Plot of 6 features: RMS, peak value, crest value, and variance, and skewness, curtices. So these are as per the figure. We can say the poor features. We can say it's skewness because it's random. It's easily to. It will difficult to decide which features belong to which area. Okay, so this is one of the disadvantage of this. So from distribution of the features, we can see we can say grouping. Okay, so data preparation for the classification. Again, the same information I'm sharing. Normal loading 0, 1, 2, inner race loading 0, 1, 2, 3, HP, ball defect 0, 1, 2, 3, outer race defect 0, 1, 2, 3, HP loading, and in each loading there are 3 fault sizes: 0.07, 0.014, 0.0221. Same repeated for the ball defect, same repeated for the outer race. Okay, so for each data divided into this training data set and testing data set, and the total data set 20 data set from normal condition, 60, 64, each of the 3 faults which generally occurs in bearing. Okay. Now this is again classification method. We can say this is the input signal. So here two scheme has been adopted. The one scheme is the raw signal is direct, the feature extracted from two scheme. The first scheme is we taken from the direct raw signal or input signal, input vibration signal. And in scheme 2 is basically the signal is passed through the wavelet packet transform and BDI, and then statistical feature calculated only for the band where the highest frequency, highest BDI is there. Okay, and we are going to compare the result of these two, scheme 1 and scheme 2. Okay, so again I'm repeating, scheme 1 is basically feature extracted from the raw signal, and scheme 2 the feature is extracted after applying the discrete wavelet transform and for the all signal, healthy, faulty and faulty signal. Okay, and try to find out the higher BDI, and from that BDI corresponding to that signal we have calculated the features. Okay, so there are two feature sets, one is from scheme 1 and another from scheme 2, and then we fed into the classifier, and then we have seen the bearing classification results. Okay. So this is training, testing, and validation, and then with the statistical parameters, statistical parameter on experimental data for scheme 1. Okay, so in scheme 1, scheme 1 means the features extracted from the raw signal. Raw signal means without any applying special signal processing techniques. Okay, the 11 features has been extracted and fed to the ANN artificial intelligence neural network. Okay, so from this this chart, from here you can observe the chart. This 5, 10, 15. These are the number of hidden neurons in the neural networks, and we can see the best obtained result is for this when hidden neurons is number of neurons is 35. Okay, so when 35 neurons, hidden neurons is there, that means hidden layers are there, that means that layer that is the giving the best results. Okay, so this is the confusion matrix from scheme 1, and we can see this the overall results of all confusion matrix. We can see total 90% result is there. It means out of 200 we can see the data set. This is 200 data set. Out of 200 data set which is corresponding to the healthy and faulty condition of the bearing. 90% data has been classified, correctly classified, when we have taken features from the raw signal. Okay, original form signal. Okay. So this is quite good enough, but we can further improve. We are going to observe by scheme 2, and we will compare these two methods. Okay. The second one is this is ROC curve. This is basically performance of ANN, and this is ROC curve, basically ratio of PPR upon FR, true positive rate divided by false positive rate. So basically, if your curve is left corner side, the more left corner side curve is there, this validation curve or ROC curve, that means that is a more accurate result. You can say more accuracy, or you can say less error is there. Okay, so if you see all ROC curve, all are basically in left side. Okay, for class 2 is the best classifier. Class 2, our ANN is classified, we can say very best, but other 3 classes, means class 2, class 3, and class 4, it has some errors. Okay, this is validation performance curve. Okay, performance means at this point you can say epochs or iteration. Okay, so what happening is basically in validation, first we do training and then validation. Validation data are those data which is not used in training. Okay, so once you train your model, and after that you have used those data which is not used in training data, so that data will give input and see the results. Okay, so and then repeating. Okay, many times it has been repeated. That is called iteration in ANN. Okay, so we can see is at 28, when 28 epoch, the error is 0.09, which is no doubt is a small result. Small error is there, but best performance is when epoch is 28 and error is 0.09. Okay, so this all for all three waveform is there: training, validation, and the testing results. Okay, so this one is the best results given. Okay, now confusion matrix for scheme 2. Scheme 2 means when we have adopted discrete wavelet transform. Okay, calculated energy of that waveform, and then we have calculated bearing damage index, and then we have find out the which bearing damage index is the high value, and corresponding to that high value we have selected that signal band, and in that signal band feature has been extracted, and that feature has been given input to the ANN classifier. Okay, so from in scheme 2 we can see our results is improved 100%. So from 90% to 100%. If you use scheme 1, the classification accuracy is 90%, but when you use scheme 2 by using a discrete wavelet packet transform, the classification accuracy result increase up to the 100%. Okay, so all we can say all testing data has been classified accurately. There is no error in testing, even not error in training, not error in validation, not error in testing, and not error in this all confusion matrix. Okay, ROC curve we can also say all curve are perfectly aligned with left corner. That means the zero error we can say we have observed a zero error in this ANN. Okay, this is epoch is high 84, but the error is too less. Okay, so this is best validation result obtained at 84 epochs. Okay, so from here we can conclude that the scheme 2 is better than the scheme 1 to get the better classification. Okay. Now the next we have tried to because number of feature is 11. Okay, so it's 11 input and 4 output. If you see the ANN diagram, so in this ANN diagram we can observe in ANN diagram we can observe the number of input is 11 and the output is 4. 4 means one is healthy, one is inner rest, one is outer rest, one is a ball defect. Okay, and input means that mean, median, peak value, crisp factor, curtices, and some dimensionless parameters are there. Okay, so 11 and 4. Okay, now our planning is to reduce the number of features. Okay, so that we can reduce the complexity at the cost of same accuracy. Okay, we are trying to find out the accuracy. Okay, again for this both the scheme 1 and scheme 2. See what happened. So in order to reduce the number of features, number of input parameters, so we have adopted that one of the popular method is principal component analysis. Okay, so by using a principal component analysis, suppose n into m matrix is there, that can be reduced into n into n matrix. Okay, and first the n matrix first column is the highest variance, and then lowest like that. So this principal component analysis can be used to detect meaningful features, we can say. So suppose 11 features are there, so all features are not meaningful. What are the meaningful features? So those features only will be used for the classification purpose. Okay. So in principal component analysis, this is a plot of first two, PC1 and PC2, because if 11 features will be there, so we will get 11 principal components. Okay, so in 11 principal component, the first two components are here we have plotted for scheme 1 and scheme 2. X-axis is basically principal component 1 and y-axis is basically principal component 2. Okay, Okay, so how we will decide the which features are meaningful? For that, we have used biplot. Okay, so in biplot, basically x-axis, y-axis is the principal component, and F1 and F2 11, F1 to F11 other features will be plotted in that in with respect to the this principal components. Okay, so how we'll identify? So this will be identify the length of the that features. Okay, so here we can see the length of the vector indicates the strength of the variable influences on the principal components. Okay, so higher the length of the variables will impact more that principal components of the data. Okay, so we can see we have drawn biplot for the scheme 1 and we have drawn biplot for the scheme 2. So from both the plots we have observed the length of the features, that is, from we have calculated that for scheme 1 the significant features are basically F4, F5, F8, because these features will have given you can say the good amount of length which affect the variables. Okay, and for scheme 2, F4, F5, F8, F3, F6, and F7 features are having the good amount of length of your features. Okay, so now the same process has been repeated with the reduced feature. So for scheme 1, from 11 features to 4 features, and from scheme 2, 11 features to 6 features. So almost you have eliminate 50% of features we have calculated earlier. Okay, so now the NN is having 4 feature for scheme 1 and 6 feature for scheme 2. Okay, and we are going to see again the results of that our ANN, artificial intelligence. Okay, so this is our result ANN. This is neurons. Okay, so from this we can see the performance of our ANN has been reduced. Okay, from scheme 1. Here we can see the confusion matrix for scheme 1, and earlier when you used 11 features, the accuracy was 91%. Sorry, it was 90%. But when we use scheme 1 with a reduced number of features, that accuracy is reduced to 81%. So it not works. Okay, so reducing the feature by using PSA, at least for reducing by using a PSA, is not worthful. Okay, because ultimately accuracy is decreased. Okay, so this is again the ROC curves. We can observe here the ROC curve accuracy of the our model is not very much appreciating. Okay. This is same validation performance curve we achieve best performance at 66 epochs and with error of 0.25, which is more than the scheme 1 when we use all the feature as a input. Okay. This is a result of scheme 2. Here result is for scheme 2 is again we have observed as 100%, and not 100%, but 99.6%. Okay, so in scheme 2, if we reduce the feature, still our result is same. Okay, so from here we can say scheme 1 is scheme 2 is better than scheme 1. Okay, so for using discrete wavelet packet transform and calculating the features is more effective, more beneficial compared to by using the only raw signal without taking any method. Okay, so here we can see the ROC curve of scheme 2 with a reduced features as a input. Okay, so from both the schemes we have done our comparison. Now the validation performance for scheme 2, again we get the at epochs of 80 and the error is 0.03, 0539. That is a error. Okay. So from this whole discussion, we have concluded that these two schemes, scheme 1 is or scheme which has scheme 1 in which feature are extracted from the raw signal, and scheme 2 in which feature are extracted based on the bearing damage index information. Okay, so in both the scheme, 11 time domain features for each has been extracted for classification purpose. Further significant feature has been obtained by applying the PCA to improve the accuracy and reduce the computational time for the classifier. Okay, so it is found when all the 11 feature has been used, scheme 1 giving 91% accuracy, and scheme 2 is given 100% accuracy when all 11 feature has been considered as an input to the classifier. Okay, by reducing the number of features, or by selecting the meaningful features by using the PCA, we have observed that scheme 1 is not performing well, but scheme 2 is again performing well with a reduced number of features. Okay, so this is the conclusions, and these are the references. These are references we can see. I have taken. Okay, so if any queries, anyone, you can ask.
इसकी फाइल अप्रूवल वाली फाइल है तुम्हारे पास इंडस्ट्री अप्रूवल जो डायरेक्टर ने दिया है वही
Hello.
Hello. हाँ sir.
Dear participants, have you any query? Please ask to sir.
Sir, in the comment box, Dev Prakash is asking for vibration signal. If possible, please provide it.
Sir, please share the hardware details of your vibration signal recording if possible. Sure, it is already available. You can. I will share the PPT with the Kamlesh sir or Santosh sir. In that, the link is there. From that link, you can get all the information.
Okay, sir, definitely. Anyone having any query, doubts? Please ask. Thank you, sir, for your such nice informative session based on your condition monitoring and bearing fault detection of induction motor. Thank you, sir, once again.
Thank you, sir. अच्छा लगा आप लोगों से फिर से मिल गया ऑनलाइन ही.
और इन फ्यूचर और भी अच्छा से करेंगे सर.
नहीं अच्छा ही है, अच्छा से क्या करेंगे.
चलिए सर, थैंक यू.
Yeah, thank you again. Listening patiently. इसको मैं कट कर दूंगा सर यहाँ से. जी. Okay, thank you sir.
Okay, thank you sir.
Thank you.
Recording stopped.